Hello there, and welcome to the Sleepy Science Channel. Tonight, we're stepping into a world hidden in petals, bark, roots, and leaves. Plant extracts may sound simple at first, yet they have been shaping our lives for thousands of years. From survival and medicine to flavors and perfumes, and even sacred rituals, they have been one of the most influential ingredients in human history. Inside a crushed leaf, a citrus peel, or a drop of resin, there is a chemistry so rich and so precise that it can cool the skin, sharpen the senses, and even control the behavior of animals. Some of these substances have changed the course of empires, while others have simply made our lives more pleasurable. And many began not for us at all, but as part of the silent struggles of plants themselves, as they defend, attract, warn, and endure. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is settle in. Let your shoulders relax and notice your eyes grow heavy. And as the day begins to gently fade away, join me as we explore this hidden chemistry of the living world together. Let's begin. Plant extracts can heal, poison, perfume, and preserve all at once. Across history, people learned that the same green world could soothe a fever, stop a heart, scent a room, or keep decay away. That is what makes plant extracts so astonishing. They are not single-purpose inventions. They are compact chemical toolkits. A resin from a tree might seal a wound and also slow the growth of microbes. A flower oil might lure pollinators in the wild, then later become part of perfume in a palace. A bitter alkaloid might defend a leaf from insects, then become a medicine in the right dose and a poison in the wrong one. Even spices in the kitchen often carry protective chemistry that once helped the plant survive heat, mold, or hungry animals. When humans learned to draw out these hidden substances, they were not creating magic from nothing. They were opening a cabinet of powers that plants have been quietly building for millions of years. A single leaf can hide hundreds of powerful chemical compounds. A leaf may look simple from a distance. Flat, green, silent, almost ordinary. Yet inside that small piece of living tissue, there can be a whole laboratory at work. Plants do not make just one useful substance. They make families of them. Some protect against fungi. Some repel insects. Some absorb sunlight safely. Some repair damage after heat or drought. Others shape scent, taste, and color. Scientists who analyze a single leaf can find an intricate crowd of molecules, each with a role, each produced at just the right place and moment. Mint leaves carry cooling compounds. Tea leaves hold bitter tannins, caffeine, and aromatic molecules that shift during processing. Even a crushed tomato leaf releases a sharp green smell because damaged cells suddenly mix chemicals that were stored apart. So, when you hold one leaf in your hand, you are not holding one ingredient. You are holding a crowded chemical city, hidden in plain sight. Humans have built medicines by studying what plants already make. Long before laboratories, people watched the living world closely. They noticed which roots eased pain, which barks lowered fevers, and which seeds were too dangerous to touch. Much of medicine began there, with human beings learning from plant chemistry step by step. Willow bark pointed the way toward familiar pain relief. Foxglove revealed compounds that could slow and steady the struggling heart. Cinchona bark offered quinine, which became one of the great anti-malarial discoveries in history. Later, chemists learned how to isolate these substances, refine them, test them, and sometimes reshape them into safer or more reliable drugs. Yet the starting point was often the same. Nature had already done the hard part. The plant had evolved a molecule with powerful effects, and humans learned how to listen. That is one reason plant extracts remain so compelling. They are not relics from the past. They are clues, and sometimes the first whisper of tomorrow's medicine. Vanilla's most famous flavor begins inside the orchid seed pod. Vanilla feels familiar now. It is in cakes, ice cream, candles, and perfumes. Yet its story begins in a plant that is anything but ordinary. Vanilla comes from an orchid, a climbing tropical vine whose flowers open only briefly. If pollination succeeds, the plant grows long green pods packed with tiny seeds and the raw materials of future aroma. Fresh from the vine, those pods do not smell like the vanilla most people know. The famous scent appears only after careful curing. Heat, drying, and time allow enzymes and stored compounds inside the pod to change. Slowly, the rich sweetness emerges. That transformation is part of what makes vanilla so captivating. It is not a flavor that simply exists, waiting to be picked. It has to be coaxed into being. Behind that soft, comforting note lies one of the most labor-intensive flavor journeys on Earth, hidden inside the fruit of an orchid most people would never recognize. Caffeine is a plant defense that humans turned into a ritual. To us, caffeine is morning. It is the first sip of coffee, the warmth of tea, the small lift that helps the world come into focus. To the plant, it began as something very different. Caffeine is defensive chemistry. In leaves and seeds, it can discourage insects and interfere with the bodies of creatures small enough to be harmed by it. Some plants even release it into the soil, where it may affect nearby growth. Yet humans encountered this bitter stimulant and did something plants never planned for. We made it social. We built ceremonies around it. Coffee houses became places of conversation, debate, and trade. Tea became linked with hospitality, discipline, and pause. Across continents, the same plant compound moved from defense into culture. That is part of its wonder. A molecule shaped by evolutionary struggle ended up woven into breakfast tables, night shifts, study sessions, and shared afternoons, quietly guiding the rhythm of modern life. Some of history's deadliest poisons began as ordinary plant extracts. Many deadly plant poisons do not come from exotic monsters of the forest. They come from leaves, seeds, roots, and flowers that can look almost harmless. That is part of what makes them so unsettling. Plants cannot run from danger, so some evolved chemistry that could stop an animal after one bite. Over time, humans learned to recognize those hidden dangers and sometimes to exploit them. Deadly nightshade carries atropine and related compounds that can disrupt vision, heartbeat, and awareness. Hemlock helped shape one of history's most famous executions. Castor beans contain ricin, one of the most feared natural toxins known. Even ornamental plants in gardens can hold potent cardiac or nerve-affecting chemicals. None of this is accidental. It is survival written in molecules. A plant with strong defenses is less likely to be eaten, stripped, or destroyed. So behind the beauty of flowers and foliage lies an ancient truth. Nature's chemistry can be elegant and merciless. The scent of roses comes from a chemical orchestra, not one note. When someone says a rose smells like a rose, it sounds simple. Yet the fragrance itself is anything but simple. Rose scent is built from many aromatic compounds rising together in shifting proportions, and that blend can change from one variety to another. Some molecules bring sweetness. Others add spice, fruit, citrus, or a faint green freshness. What reaches your nose as one seamless perfume is really a layered performance, with each chemical adding depth, brightness, softness, or lift. Temperature matters. Time of day matters. Even the stage of the bloom matters. A rose opening in cool morning air may smell different by afternoon. This complexity is why rose perfume has fascinated growers, distillers, and chemists for centuries. They are not chasing one ingredient. They are trying to capture an accord so balanced that the mind reads it as effortless beauty. Behind that familiar floral breath is a remarkable act of natural composition, precise as music. Tiny amounts of plant extract can transform food, mood, and memory. Some of the most powerful effects in daily life arrive in vanishingly small amounts. A few drops of vanilla can change a batter from flat to inviting. A trace of mint can make water taste colder than it is. The scent of orange peel or crushed basil can alter how a room feels before anyone says a word. Plant extracts work this way because our senses are exquisitely sensitive to certain molecules. They do not need much. A little can awaken appetite, comfort, nostalgia, alertness, or calm. Smell is especially powerful because it is closely tied to memory. One fragrance can pull a person toward a kitchen from childhood, a garden after rain, or a holiday table long gone. That is why plant chemistry feels larger than its size. Tiny quantities can reshape experience itself. They can change what food tastes like, how a space feels, and which forgotten parts of life suddenly come rushing back. Many plant extracts evolved first as weapons in nature's silent wars. Plants may seem passive, but they live in constant conflict. They are chewed, pierced, infected, shaded, crowded, and attacked from every side. Because they cannot flee, many evolved chemistry as a form of warfare. Bitter alkaloids discourage herbivores. Sharp sulfur compounds burst into action when tissues are damaged. Sticky resins trap insects and seal wounds. Some roots release substances into the soil that make life harder for nearby rivals. Other plants send airborne signals after an attack, warning their neighbors that danger is close. Seen this way, a forest or meadow is not chemically peaceful at all. It is full of defenses, traps, alarms, and countermeasures moving through air, sap, bark, and leaf. This is where so many plant extracts began. Not as flavorings, remedies, or perfumes for human use, but as survival tools forged in endless evolutionary pressure. We entered the story later, discovering that nature's weapons could also become medicine, spice, and scent. Mint feels cold because its extract tricks your nerves. When mint touches your tongue or skin, nothing actually becomes colder. Instead, menthol binds to receptors that normally respond to a drop in temperature, and your nervous system reports coolness even when the air or liquid stays the same. That is why mint can make chewing gum feel icy, toothpaste feel fresh, and a breeze across mentholated skin feel suddenly sharper. It is a chemical illusion, but a very convincing one. Plants did not evolve this sensation to brighten human breath. Mint likely uses menthol and related compounds as protection, making itself less appealing to insects and animals. Yet to us, the effect feels clean, vivid, and strangely invigorating. One small leaf can therefore rewrite your sensory world for a moment. It can persuade the body that cold has arrived out of nowhere, proving that plant extracts do not just flavor experience. Sometimes they edit perception itself, right at the level of the nerves. Chilly heat comes from a plant compound that mammals learn to fear. The fire in a chili is not a taste in the ordinary sense. It is pain. Capsaicin binds to the same receptors that respond to dangerous heat, so your mouth reacts as though it has touched something burning. Your heart may quicken. Your eyes may water. Your skin may flush. For the plant, this was a clever move. Mammals tend to crush seeds with their teeth, which destroys the plant's future. Birds do not sense capsaicin the same way, so they can swallow the fruit and carry the seeds elsewhere. In other words, the pepper found a way to discourage the wrong dinos and welcome the right ones. Humans complicated the story. We turned that warning signal into cuisine, competition, and craving. We chase the burn, sweat through it, and come back for more. Few plant extracts show human defiance more clearly than the chili, which began as a deterrent and became delight. Lavender extract can influence insects long before humans smell it. Before lavender became associated with linen, soap, and evening calm, its fragrance was already shaping the lives of much smaller creatures. The oils rising from its flowers are signals in the insect world. Some help guide pollinators toward nectar. Others discourage pests or interfere with insects that might feed on the plant. To a bee, the scent is not a decorative extra. It is part of a map. To a hungry herbivore, it can be a warning. What humans notice as softness or freshness is therefore only one layer of a much older biological language. Lavender is broadcasting constantly, and insects are among the first to hear it. That hidden conversation is part of what makes the plant so captivating. A calm-smelling bloom in a garden is also an active chemical beacon, negotiating with pollinators, warding off trouble, and managing its place in the landscape. Its perfume reaches us last, after evolution has already assigned it work. Nicotine is a plant insecticide that also hooks the human brain. Tobacco did not evolve nicotine for human fascination. It evolved it as a weapon. In insects, nicotine can attack the nervous system with brutal efficiency, overwhelming the same kind of signaling pathways that living bodies depend on to move and survive. That made it an effective defense in the ancient contest between leaf and predator. Humans discovered the same molecule and found that, in smaller doses, it could sharpen attention, alter mood, and create a rapid feeling of reward. The reason lies in the brain, where nicotine can mimic one of the body's own signaling chemicals and trigger pathways linked to pleasure, learning, and repetition. That is how plant defense became one of history's most powerful human habits. It crossed from field to culture, from ecology to addiction, carrying both stimulation and danger in the same compact structure. Few extracts show more clearly how a molecule can be useful, seductive, and destructive without ever changing its basic nature. Quinine from bark once helped humanity battle malaria. There was a time when vast parts of the world were haunted by a fever that seemed almost inescapable. Malaria could hollow out armies, stall trade, and make whole landscapes deadly to enter. Then came bark from the cinchona tree, carried from the Andes and prized for the bitter compound hidden inside it. Quinine did not end malaria, but it gave people a powerful tool against one of history's great killers. That changed exploration, empire, medicine, and survival itself. Travelers, soldiers, and doctors all came to depend on a substance drawn from a tree that had evolved its chemistry for reasons of its own. The taste was harsh, but the effect could be life-saving. Even tonic water carries a faint echo of that story. Behind its bitterness lies a chapter in which plant extraction helped humans push back against disease and move through regions that had once seemed nearly impossible to endure. Foxglove compounds changed heart medicine by slowing a failing pulse. Foxglove is one of those plants that seems almost theatrical. Tall spikes of purple flowers rise from the ground with a beauty that invites admiration. Yet inside the plant are compounds powerful enough to alter the rhythm of the human heart. In carefully controlled doses, substances derived from foxglove helped doctors strengthen weak contractions and slow certain dangerously rapid heartbeats. That was a profound discovery, because it revealed that a failing pulse could sometimes be steadied by chemistry hidden in a garden flower. The margin for error, however, is small. Too much can become dangerous very quickly. That tension gave foxglove a special place in medical history, poised between remedy and risk. It showed that the line between healing and harm is often measured not in different substances, but in different amounts. Few examples capture the drama of plant extracts more vividly than this. A blossom that looks almost storybook gentle can reach directly into the machinery of life. The rosy pink of grapefruit comes with unusually bitter chemistry. Grapefruit arrives with bright color, fresh scent, and the promise of sweetness, yet the first bite often carries a surprise. Beneath the juicy brightness lies an assertive bitterness that sets it apart from most other citrus fruits. That character comes from compounds such as narration, which give grapefruit much of its unmistakable edge. It is one reason the fruit feels more adult than playful, less like candy, and more like a deliberate awakening of the palate. But grapefruit chemistry is fascinating for another reason too. Its extracts can interact with enzymes in the body that help process certain medicines, sometimes changing how strongly those medicines act. So this breakfast fruit is not chemically simple at all. It is a vivid reminder that flavor and physiology can meet in unexpected ways. A pink wedge on a plate can carry beauty, bitterness, and biological consequence together, turning an ordinary kitchen moment into something far more chemically dramatic. Tea leaves hold different extracts depending on how they are processed. Black tea, green tea, white tea, and oolong can taste so different that they seem to come from separate plants, yet many begin as leaves from the same species. What changes the experience is processing. Once picked, the leaves may be heated quickly to halt certain reactions, or they may be allowed to oxidize, curl, darken, and transform. During that journey, the balance of extracted compounds shifts. Fresh, grassy notes may soften. Floral hints may deepen. Tannins may become rounder or more pronounced. New aromatic molecules can appear as the leaf's chemistry rearranges itself after harvest. This is what makes tea so enchanting. It is not just a plant ingredient dropped into hot water. It is a record of choices made after picking, each one shaping what your cup will become. The same hillside leaf can end as something brisk, smoky, buttery, floral, malty, or deep, depending on how human hands guide its chemistry. Coffee aroma comes from hundreds of compounds released after roasting. A coffee bean before roasting does not smell like the brew people line up for each morning. The famous aroma is born in heat. As the beans roast, sugars, acids, proteins, and other stored compounds begin to react in waves, generating a dense cloud of new molecules. Some smell nutty. Some smell caramel, like fruity, smoky, chocolatey, spicy, or even faintly floral. Together they create one of the most complex everyday aromas on Earth. That is why coffee can feel so rich before you even taste it. The scent is layered, and the brain starts reading those layers instantly. Roasting level changes the whole performance. A lighter roast may preserve bright and delicate notes, while darker roasting can push the chemistry toward bitterness, depth, and smoke. What makes this remarkable is how much transformation is involved. The raw seed contains the potential, but the smell that fills a kitchen at dawn is really the sound of chemistry being unlocked by fire. The taste of almond can hint at surprisingly dangerous chemistry. Almond flavor often suggests comfort, sweetness, and dessert. Yet one of its signature notes shares chemical territory with something far darker. Bitter almonds contain compounds that can break down to release hydrogen cyanide, a substance feared for good reason. Sweet almonds, the kind people usually eat, are bred to avoid that danger and can be enjoyed safely. But the deeper story remains. Plants in this family evolved a way to pack their seeds with defensive chemistry that becomes threatening when tissues are crushed and enzymes begin to act. The familiar marzipan-like aroma linked with almond can therefore carry an unsettling echo of toxicity. It is a reminder that pleasant smell and danger do not always live far apart. Nature often hides warning and attraction in the same place. Few flavors reveal the duality so elegantly. Something associated with cakes and pastries turns out to belong to a much older chemical strategy, built for defense rather than delight. Willow bark helped inspire one of the world's most familiar painkillers. For centuries, people noticed that willow bark could ease pain and reduce fever. That old observation eventually helped guide one of the most famous medical stories in modern life. Willow contains salicin, a compound that the body can convert into related forms with pain-relieving effects. Over time, chemists studied that natural chemistry and searched for ways to keep the benefits while reducing the harshness that older preparations could cause. The result was not a simple copy of the bark itself, but an inspired descendant of it, refined through science into something far more consistent and widely used. What makes this story so compelling is the bridge it reveals between folk knowledge and modern medicine. A tree growing beside watercourses and riverbanks became part of a chain of insight that reached the pharmacy shelf. It is a reminder that many breakthroughs do not begin with steel and glass. They begin with bark, bitterness, attention, and time. Turmeric's golden extract became one of nature's most studied pigments. Turmeric stains fingertips, cutting boards, and cooking spoons with a yellow so intense it seems almost to glow from within. The compound behind that famous color is curcumin, a plant pigment but has fascinated cooks, healers, chemists, and medical researchers for generations. It helped make curries radiant, robes luminous, and food instantly recognizable across whole culinary traditions. Yet the story goes beyond color. Curcumin became one of the most closely examined plant compounds in modern research because scientists wanted to understand its behavior in the body and its possible biological effects. That curiosity turned a kitchen spice into a laboratory regular. Even so, turmeric's most immediate wonder may still be sensory. A dry, knotted root holds a color powerful enough to transform an entire dish with a small spoonful. It is hard not to be captivated by that. One underground stem stores a pigment that can feel like concentrated sunlight, drawn up from soil and fixed into spice. Saffron's color, taste, and scent come from different molecules. Saffron is one of the clearest proofs that a plant extract can be lavishly complex. Its deep golden color, its hay-like sweetness, and its almost haunting perfume do not come from one master ingredient. They come from different molecules working together. Crozin brings the vivid color that spreads through rice, broth, and cream like liquid gold. Picrocrosin contributes the distinctive bitter edge that keeps saffron from tasting merely sweet. Saffronel rises into the air as the aroma most people recognize, warm, delicate, and hard to compare with anything else. All of this is concentrated in the dried stigmas of a crocus flower, each one tiny and fragile. That is part of the wonder. Such a grand sensory effect begins in thread-like structures that must be gathered by hand. Saffron does not overwhelm by force. It reveals itself in layers, showing how one flower can divide beauty among color, taste, and scent with astonishing precision. Clove extract can numb pain while smelling warm and sweet. A clove scent suggests comfort at first. It is warm, rich, and almost festive. The kind of aroma that seems to belong in baked fruit, spiced drinks, and winter kitchens. Yet the same bud contains eugenol, a powerful compound with a very different talent. It can numb tissue and dull pain, which is why clove oil has long been associated with aching teeth and sore gums. Few spices reveal such a striking contrast between fragrance and function. Something that smells welcoming can also act with real force on the body. That dual nature helps explain the long fascination with cloves in trade, medicine, and cooking. They are not just flavor. They are concentrated chemistry wrapped in a dried flower bud. When you taste or smell clove, you are encountering a plant substance that can comfort the senses and influence pain at the same time. It is one of the clearest reminders that spice and medicine have always overlapped. Eucalyptus leaves release vapors that can shape the air around them. Stand beneath a eucalyptus on a warm day, and the air itself seems different. Sharper, cleaner, almost medicinal. That feeling comes from volatile compounds rising from the leaves, especially cineal and other aromatic molecules that evaporate readily into the surrounding air. These vapors may help the tree deter herbivores, limit microbial growth, and cope with harsh, dry conditions. To us, they create an atmosphere strong enough to feel physical, as though the space has been altered rather than merely scented. Entire groves can carry that effect, especially in heat, when the leaves release more of their chemistry into the breeze. Eucalyptus therefore becomes more than a tree you look at. It becomes a tree you enter. Its presence expands into the air and changes the character of a place. Few plant extracts feel so environmental. Instead of staying locked inside bark or leaf, they drift outward and turn the space around the plant into part of its living chemical signature. Some plant extracts only appear after the leaf is damaged. Many plants keep key ingredients separated inside their tissues, like components of a trap waiting to be sprung. As long as the leaf remains whole, the chemistry stays quiet. But when an insect bites, a hoof tears, or human fingers crush the surface, barriers break, enzymes meet stored molecules, and entirely new compounds can appear within seconds. This is one of the cleverest strategies in the plant world. It lets the plant avoid wasting energy on constant chemical production while still unleashing a potent response at the moment of attack. The smell of damage, the burst of bitterness, or the sudden rise of a deterrent may all be part of that instant transformation. In other words, the plant becomes more chemically active when it is wounded. That is a startling thought. Injury is not only harm, it can be a trigger. The leaf changes its chemistry in real time, turning destruction into a rapid act of defense the moment it is touched. Garlic becomes chemically stronger only after you crush it. A whole garlic clove is full of potential, but much of its famous force lies dormant until the structure is broken. Inside the intact cells, crucial ingredients are kept apart. Chop, crush, or grate the clove, and those components finally meet. An enzyme gets to work, and within moments new sulfur-rich compounds begin to form, including allicin, which gives fresh garlic much of its fierce aroma and bite. That is why a smashed clove smells sharper than an untouched one, and why chopped garlic can seem to bloom in strength right on the cutting board. It is chemistry triggered by injury, fast and dramatic. For the plant, this likely served as protection against microbes and hungry attackers. For us, it became one of the great transformations in the kitchen. A pale, quiet clove can suddenly flood a room with scent and promise. Few ingredients demonstrate more clearly that the real character of a plant may wait until the moment it is broken. Freshly cut grass smells green because plants send chemical alarms. That smell drifting across a freshly mown lawn seems clean, bright, and strangely peaceful. Yet to the plants themselves, it is a distress signal. When grass blades are cut, damaged cells release a burst of volatile compounds, often called green leaf volatiles. These molecules create the crisp scent humans associate with summer, but in the plant world, they can serve as alarms. They may help warn nearby tissues, prepare defenses, or attract predators that attack the insects doing the damage. What feels soothing to us is therefore part of a rapid emergency broadcast. That reversal is one of the most captivating things about plant extracts. Human pleasure can be built on a plant's crisis chemistry. The lawn smells alive because it has been injured, and the air fills with molecules that carry urgent information from one blade to another. A calm suburban fragrance turns out to be a message of trouble, released in an instant and carried on the breeze. Pine forests perfume the air with extracts meant for defense. The scent of a pine forest feels almost cleansing, as though the trees are washing the air with resin and light. That famous aroma comes largely from terpenes released by needles, bark, and resin, compounds that help pines defend themselves against insects, pathogens, and environmental stress. Some rise steadily in warm weather. Others pour out more dramatically when bark is wounded, and sticky resin seals the injury. To us, the result is invigorating. To the tree, it is strategy. Those fragrant molecules can gum up invaders, discourage feeding, and help protect damaged tissue from infection. Entire woodlands therefore breathe defense into the atmosphere every day. That is part of why pine forests feel so distinctive. Their chemistry is not hidden deep inside a fruit or flower. It drifts around you with every step. The sharp freshness in mountain air is also a reminder that trees are active participants in their own survival, shaping the forest through scent as well as wood. Many floral scents are really advertisements aimed at pollinators. A flower's perfume can seem like pure beauty, yet in evolutionary terms, it is often marketing. Plants invest energy in scent because they need visitors, and fragrance helps guide those visitors to nectar, pollen, and the exact structure of the bloom. Different pollinators prefer different signals. Bees often respond to one set of aromatic cues. Moths may be drawn to stronger evening scents that travel through the dark. Flies can be lured by odors humans find foul, while bats may follow heavy, musky notes after sunset. This means a flower's fragrance is not just pleasant decoration. It is targeted communication, shaped by who the plant wants to attract and when those partners are active. Once you know that, a garden changes completely. The air becomes crowded with invitations, bargains, and promises drifting from petal to petal. What humans call lovely may simply be effective. The bloom is not trying to enchant us first. It is trying to secure the next generation. Bitter plant extracts often evolved to stop animals eating leaves. Bitterness is one of nature's oldest warning systems. For many animals, including humans, a strongly bitter taste suggests caution because it can signal the presence of toxic or biologically active compounds. Plants have taken full advantage of that response. By loading leaves, bark, or seeds with bitter molecules, they make themselves less appealing to creatures that might otherwise eat them down to the stem. Alkaloids, tannins, and many other defensive substances can all contribute to this effect. Some merely taste unpleasant. Others interfere with digestion, damage tissues, or disrupt the nervous system if an animal ignores the warning. That is why bitterness is so widespread in the plant world. It is not a flaw in flavor. It is survival made perceptible on the tongue. Humans, of course, complicate matters again. We learn to enjoy some bitterness in tea, coffee, herbs, and tonic drinks. Even so, the ancient message remains underneath. The plant is still saying, think carefully before taking another bite. Sweet plant extracts can persuade animals to carry seeds away. Plants cannot walk their offspring into new territory, so many learned a more elegant trick. They wrapped seeds in sweetness and let animals do the traveling. Sugars, fruity aromas, and vivid pigments work together as invitations, turning a ripe fruit into a moving contract. Eat this and carry my future elsewhere. Birds swallow berries and later drop the seeds miles away. Mammals strip figs, dates, and plums from branches, then scatter the hard cores beyond the parent plant's shadow. This strategy is remarkably precise. The soft outer flesh is designed to be desirable, while the seed itself is built to survive chewing, digestion, or both. In many species, passing through an animal can even help trigger germination later on. So the sweetness of fruit is not generosity. It is engineering. What tastes like abundance to us often began as a transport system, built by plants to recruit hungry creatures into the long work of dispersal. Peppermint and spearmint differ because of one subtle chemical shift. Peppermint and spearmint are close enough to seem almost like two accents of the same flavor, yet a small change in chemistry sends them in very different directions. Peppermint is dominated by menthol, which delivers that forceful cooling sensation people associate with strong gum, toothpaste, and medicinal freshness. Spearmint leans more on carvone, a compound that feels softer, sweeter, and more herbal, with far less icy bite. The difference sounds minor when described on paper, but in the mouth, it feels dramatic. One races across the nerves like a cold wind. The other lingers in a greener, rounder way that suits cooking and confectionery beautifully. This is one of the marvels of plant extracts. A close botanical relationship does not guarantee the same sensory world. A subtle shift in which molecules are emphasized can turn a familiar leaf from brisk and piercing into smooth and approachable, as though two neighboring plants had learned entirely different ways to introduce themselves. Basil can smell like cloves, lemons, or anise, depending on variety. Basil is not one single scent wearing different labels. It is more like a whole family of aromatic personalities gathered under one name. Some varieties lean toward clove like warmth because they carry more eugenol. Others sparkle with citrus notes from compounds that feel bright and almost fizzy to the nose. Still others drift toward anise, with sweet herbal tones that seem to belong in both gardens and pastry shops. This variety is what makes basil so intriguing to growers, cooks, and perfumers alike. The leaf shape may change only a little, yet the extracted aroma can move in surprisingly different directions. A handful torn into a salad may smell peppery and floral in one kitchen, then soft and lemony in another. That means basil is not just a herb. It is a reminder that plant chemistry can branch into multiple sensory identities inside one species, each one shaped by genetics, climate, and careful selection. Citrus peel stores fragrant oils in thousands of tiny bursting pockets. The skin of an orange or lemon seems smooth from a distance, but up close it is packed with miniature reservoirs of volatile oil. Press or twist the peel, and those little sacs rupture, releasing a visible mist so fragrant it can fill the air in an instant. That burst is one of the most immediate demonstrations of plant chemistry you can witness in a kitchen. The aroma is not hiding deep in the fruit. It is waiting at the surface, stored under pressure in countless microscopic pockets built into the rind. For the plant, these oils likely help defend the fruit against pests and pathogens. For us, they become perfume, flavor, and spectacle. A strip of peel expressed over a drink can transform the entire glass before it even touches the lips. Few ingredients reveal their inner workings so dramatically. One quick twist, and the fruit answers with a cloud of concentrated sunlight and scent. Lemon extract smells bright because it is chemically rich in limonene. Lemon seems to smell like brightness itself, as if freshness could be turned into an aroma and poured into the air. Much of that effect comes from limonene, a volatile compound abundant in citrus peel that delivers a clean, sparkling character the brain reads as vivid and lively. It is not sweetness in the way vanilla is sweet, and it is not floral like rose. It feels sharper, faster, almost visual. That is why lemon fragrance appears in kitchens, cleaning products, perfumes, and candies that want to suggest energy and clarity. Yet the story is not just about one cheerful scent. Limonene exists because the fruit evolved a complex chemical barrier at its surface, one that helps protect the peel while also making the fruit unmistakable in the world. So when a lemon is zested or peeled, what rushes out is not just pleasant smell. It is a defensive outer chemistry that humans came to associate with light, cleanliness, and sudden awakening. Orange blossom and orange peel smell different from the same tree. It is easy to assume a tree should have one signature scent, yet the orange tree tells a more layered story. Its blossoms release a soft, luminous fragrance that feels airy, floral, and almost creamy. The peel of its fruit, by contrast, erupts with sharp citrus oils that feel brisk, juicy, and immediate. Same tree, entirely different aromatic worlds. That contrast exists because flowers and fruits are solving different problems. The blossom needs to attract pollinators with delicacy and precision. The peel must protect a developing fruit with a tougher arsenal of volatile compounds stored in its rind. So one part of the tree whispers, while another flashes. Perfumers have prized this distinction for centuries, capturing neroli and orange flower water from the blooms, while cooks and distillers turn to zest and peel for brightness. The orange tree therefore becomes a kind of living lesson in plant chemistry, proving that one organism can speak in multiple scents at once. Grapes contain hidden aroma compounds that fermentation can unlock. A fresh grape can taste simple, juicy, and sweet, but inside it are chemical possibilities that may not fully reveal themselves until yeast enters the story. During fermentation, sugars vanish, alcohol appears, acids shift, and a whole hidden world of aroma begins to unfold. Some compounds are released from bound forms that had little scent in the intact fruit. Others are transformed by yeast metabolism into notes that can suggest flowers, stone fruit, spice, herbs, smoke, or earth. That is why wine can smell far more intricate than the grapes from which it came. Fermentation is not just preservation. It is revelation. The fruit arrives carrying locked doors, and the microbial process begins opening them one by one. What emerges can vary dramatically with grape variety, climate, skin contact, and the strains of yeast involved. So a vineyard is not only producing sweetness for harvest, it is also growing the hidden ingredients of aromas that may not exist until the fruit is changed. Hops give beer bitterness through extracts once meant for protection. The bitterness in beer can feel refined, refreshing, even addictive in the best sense, yet the plant behind it evolved those compounds for a far less festive purpose. Hops produce bitter acids and aromatic resins that help defend the cones from pests and microbial threats. Humans discovered that these same extracts could transform brewing. They added structure to the flavor, balanced sweetness from malt, and helped beer keep longer by discouraging spoilage. That combination changed brewing history. Hops did not simply season beer. They reshaped what beer could be. Their chemistry allowed brewers to create drinks with sharper definition, greater stability, and whole new ranges of aroma, from piney and resinous to citrusy, floral, or tropical, depending on variety and handling. Every bitter finish, therefore, carries an ecological backstory. What tastes crisp in a glass began as a plant survival toolkit, recruited into one of the world's most enduring and inventive fermentation traditions. Cinnamon's warmth comes from bark, not from wood itself. Cinnamon feels like a flavor made for memory. It clings to pastries, warm drinks, and winter kitchens with a sweetness that seems almost glowing. Yet that famous character does not come from the tree's wood. It comes from the inner bark, which is harvested, dried, and curled into quills as its aromatic compounds concentrate and settle. The dominant note comes from cinnamaldehyde, a substance powerful enough to define the spice almost on its own, though other molecules add depth and complexity around it. This matters because it reminds us how specific plant extraction can be. Not every part of a plant tells the same story. In the same trunk, one layer becomes lumber, another becomes perfume and flavor. The bark is where defense and aroma meet. It protects the living tissues beneath, while also storing chemistry humans learned to treasure across trade routes and centuries. A cinnamon stick is therefore not carved wood. It is the fragrant skin of a tree. Black pepper's bite comes from a remarkably stable plant compound. Black pepper does not burn like chili, and it does not cool like mint. Its effect is something distinct, a dry, warm, persistent bite that seems to spread slowly across the mouth. That sensation comes mainly from piperine, a compound notable not only for its flavor, but for its stability. Unlike some delicate aromas that vanish quickly with heat or time, piperine holds on well enough to make pepper useful across countless dishes and conditions. It survives grinding, cooking, and transport with impressive persistence, which helps explain why pepper became one of the world's great trading spices. Tiny, dark berries from a climbing vine could travel far, and still deliver their unmistakable spark. The plant likely evolved that chemistry as a deterrent to herbivores and attackers, but humans heard something else in it. We tasted warmth, liveliness, and depth. In one small peppercorn, defense chemistry became one of the most universal seasonings on Earth. Cardamom packs intense fragrance into seeds smaller than a fingernail. Cardamom is one of those spices that feels almost disproportionate to its size. Crack open the pod and inside are tiny dark seeds, each one carrying an aroma so concentrated it can reshape an entire pot of tea, a pan of rice, or a tray of pastries. The fragrance is difficult to pin down neatly because it moves in several directions at once. It can seem citrusy, cool, resinous, sweet, and spicy in the same breath. That complexity comes from a dense blend of volatile compounds stored in minute amounts of seed tissue. The scale of it is astonishing. Something smaller than a fingernail can perfume a room. That is why cardamom has long been treasured in cuisines and trade networks spanning enormous distances. It offers intensity without heaviness, lift without sharpness. Few plant extracts show such efficiency. The pod looks modest, but once broken, it releases a fragrance that feels far larger than the plant structure that contained it. Coriander seeds and coriander leaves taste almost like different plants. Few culinary plants create more surprise than coriander, because its leaves and seeds can seem to belong to separate worlds. The fresh leaves offer a vivid green character that many people find bright and exhilarating, while others experience them as soapy or harsh due to differences in scent perception. The dried seeds move in another direction entirely. They are warmer, nuttier, and often touched with citrus, like sweetness once toasted or ground. Same plant, dramatically different expression. This happens because the chemistry of the leafy tissues is not the chemistry of the mature fruiting structures. Different compounds dominate at different stages and in different organs. The plant is changing its sensory language as it moves through life. That makes coriander more than a seasoning. It becomes a small lesson in botanical complexity. A single species can offer two nearly separate flavor identities, one vivid and divisive, the other rounder and widely loved, all without changing its name. Fennel extract can smell sweetly medicinal because of a neat hole. Fennel carries a scent that many people recognize before they can name it. It is sweet, herbal, and slightly cool, with a character that drifts toward old cough sweets, liqueurs, and apothecary jars. Much of that identity comes from anethole, a compound powerful enough to define fennel's aroma, while also appearing in a few other plants known for similar notes. The effect is fascinating because it sits between comfort and intensity. It can feel food-like in one setting, medicinal in another, and almost perfumed in a third. That flexibility has helped fennel travel through kitchens and remedies for centuries. Seeds, fronds, and bulbs all carry some version of its identity, though in different balances and textures. When extracted or crushed, the sweetness comes forward with remarkable clarity. It is one of those plant signatures that seems almost designed for memory. A trace can call up bread, herbal tea, sweets, or medicine with unusual speed. Star anise and fennel share a surprising flavor molecule. At first glance, star anise and fennel seem like strangers. One comes as a dark, star-shaped fruit with a dramatic appearance. The other arrives as feathery fronds, seeds, or a pale bulb from the garden. Yet the moment their aromas rise, the kinship becomes clear. Both are rich in anethole, the same flavor molecule that gives them that sweet, licorice-like signature. This shared chemistry is a beautiful example of how different plants can converge on a similar sensory effect. They need not be close twins in form or culinary role to produce a familiar note in the mind. That is why star anise can echo fennel in broths, teas, sweets, and spice blends, while still bringing its own darker, more resinous character to the mix. beneath the surface, the two are speaking the same molecular language. It is a reminder that plant flavor is not always about appearance or ancestry first. Sometimes chemistry creates the family resemblance. Rosemary extract can help slow the spoilage of fats. Rosemary is easy to admire for its piney, savory aroma, but one of its most practical talents is less obvious. Compounds within the plant can help protect fats from oxidation, the process that leads oils and rich foods toward rancid, stale flavors. In other words, rosemary does not only season food, it can help preserve it. That makes perfect sense in the plant's own life. A shrub growing under strong sun and dry conditions benefits from chemistry that can manage stress and protect living tissues. Humans learn to borrow that advantage. Extracts of rosemary have been used to help stabilize foods, especially those rich in oils, without relying solely on synthetic additives. It is one more example of a flavoring herb doing hidden work behind the scenes. The scent in a roasting pan may be the most obvious contribution, but another part of the plant's chemistry is quietly defending freshness. A fragrant needle leaf becomes a guardian against thyme and air. Thyme's sharp scent comes from compounds plants use against microbes. Thyme smells clean in a way that feels almost surgical, as though the herb carries brightness and seriousness in the same breath. That quality reflects the role of compounds such as thymol, which help the plant defend itself against microbes and other threats in the challenging environments where thyme often grows. The aroma is therefore not decorative. It is active chemistry with a defensive purpose. Humans noticed that power long ago. Thyme found a place not only in cooking but in older traditions of preservation, cleansing, and herbal use, because its scent hinted at something strong beneath the surface. Even a small pinch can dominate a dish, cutting through richness with remarkable precision. That intensity comes from a plant that lives exposed to heat, dryness, and attack, and answers with concentrated protection in its leaves. When thyme rises from a hot pan or crushed sprig, what you are smelling is a small Mediterranean defense system, translated into flavor. Sage leaves are crowded with oils built for harsh, dry climates. Run a finger over sage, and the leaf already feels different from many herbs. It is soft, textured, almost velvety, as though it were built to hold onto itself in difficult weather. Inside those leaves lies an equally purposeful chemistry. Sage stores a rich blend of aromatic oils that help it endure hot sun, dryness, and the constant pressure of hungry insects or invading microbes. The result for us is a fragrance that feels broad, earthy, and slightly camphor-like, with enough strength to anchor butter, meat, stuffing, or tea. Yet behind that culinary depth is a survival story. Plants growing in demanding climates often invest heavily in protective compounds, and sage is a wonderful example of that strategy. Its leaves are not merely flavorful by accident. They are packed with chemistry because the plant must endure and defend itself in exposed conditions. What reaches the kitchen is therefore a concentrated memory of sun, stress, and resilience. Oregano extract is so potent because its chemistry is highly defensive. Oregano can seem almost oversized for an herb. A small pinch can fill a sauce, rise through steam, and linger in the air long after the pot is off the heat. That force comes from a chemistry loaded with defensive intent. Compounds such as carvacrol and others in its aromatic profile help protect the plant against microbes, grazers, and environmental pressure. In the wild, that potency serves survival. In the kitchen, it translates into one of the most assertive and recognizable herb flavors people know. This is why oregano feels so immediate. It does not creep gently into a dish. It arrives with conviction. Even dried, it can hold on to remarkable intensity because the underlying chemistry is robust. That strength made oregano especially valuable in cuisines that depend on herbs able to survive sun, storage, and long cooking. What tastes bold in tomato sauce or on roasted vegetables began as a concentrated botanical defense, adapted beautifully into flavor. Bay leaves flavor slowly because their extracts release with heat. A bay leaf often looks too modest to matter. Slip one into a pot, and at first it seems to do almost nothing. But time and heat change that impression completely. As the leaf simmers, its aromatic compounds begin to loosen and move into the surrounding liquid, releasing a layered flavor that is subtle but unmistakably structural. Bay does not shout like oregano or arrive instantly like citrus peel. It works more like an infusion, slowly building depth, dryness, and a certain haunting herbal lift that is hard to identify until it is missing. This gradual release is part of its charm. The leaf is built to hold its chemistry tightly, which suits a plant living through changing conditions. Cooking coaxes those compounds out with patience rather than force. That makes bay one of the great examples of hidden plant power. What seems like a dry, stiff leaf becomes, given warmth and time, an architect of flavor moving quietly through the whole dish. Vanilla must be cured carefully before its signature extract appears. Freshly harvested vanilla pods can surprise people because they do not smell richly of vanilla at first. The famous aroma most people know is not waiting there fully formed. It emerges through curing, a controlled process of sweating, drying, resting, and gradual chemical transformation. During that period, enzymes and stored precursors inside the pod begin to change, and vanillin rises into prominence, along with many supporting compounds that give real vanilla its depth. This means vanilla is not simply harvested. It is developed. Human skill becomes part of the flavor, guiding the pod through a slow conversion from green and quiet to dark, fragrant, and deeply complex. That journey is one reason vanilla became so prized. Its sweetness is not cheap or effortless. It is the result of patience, labor, and delicate timing. Behind every soft, familiar note lies an orchid fruit that had to be persuaded over weeks and months to reveal the scent the world now knows instantly. Cocoa beans taste nothing like chocolate until chemistry transforms them. Fresh cocoa beans do not taste like the smooth, familiar chocolate people imagine. Straight from the pod, they are bitter, sharp, and surrounded by sweet pulp, with very little of the deep aroma that later defines cocoa. The transformation begins after harvest, when the beans are fermented beneath leaves or in boxes, warmed by microbes feeding on the pulp. That process changes the chemistry inside the seed, reducing harshness and creating the precursors of future flavor. Then comes drying, roasting, and grinding. Heat drives further reactions, building the nutty, rich, roasted notes people recognize instantly. Chocolate, in other words, is not simply found. It is developed through carefully guided change. A tropical seed packed with defensive bitterness becomes one of the world's great indulgences, only after microbes, time, and fire have done their work. Few plant products show this more dramatically. The bean begins almost unrecognizable, then becomes a flavor millions of people crave. Tea tannins can make your mouth feel dry on contact. That dry, gripping feeling strong tea can leave behind is not dehydration. It is chemistry unfolding right on the surfaces of your mouth. Tea contains tannins, plant compounds that bind to proteins in saliva. When that happens, the lubricating slickness of the mouth changes, and the tongue suddenly feels rougher, tighter, and drier than before. The sensation can be delicate in a lightly brewed cup, or strikingly firm in a darker, stronger infusion. This is one reason tea has such structure. It is not only flavor and aroma. It has texture, and that texture comes from plant chemistry, interacting with the body in real time. The effect also helps explain why milk, sugar, or shorter brewing can change the experience so much. They soften the grip. What seems at first like a simple drink is therefore performing something surprisingly physical, turning dissolved leaf compounds into a tactile event that lingers long after the sip itself has gone. Oak bark is rich in tannins once used to turn hides into leather. For much of human history, oak was more than timber and shade. Its bark held tannins so powerful that they helped transform animal hides into leather, turning something that would otherwise rot into a durable material fit for shoes, belts, saddles, and books. The process worked because tannins bind to proteins, strengthening and stabilizing the hide in a way that resists decay. That means an extract evolved by a tree for protection became central to one of the great crafts of civilization. Tanneries once relied on stripped bark, ground, and soaked until its chemistry could seep into the hides and slowly change them. It was slow work, often harsh and labor-intensive, yet it connected forest chemistry to daily human life in an intimate way. A tree growing quietly at the woodland edge could end up shaping clothing, travel, and trade. Few examples show more clearly how plant extracts moved from ecology into the foundations of material culture. Pomegranate rind carries extracts far more astringent than its juice. The bright juice of a pomegranate feels lush and jewel-like, but the fruit's outer layers tell a tougher story. Its rind and inner membranes contain much higher levels of astringent compounds than the sweet-tart arils people usually eat. Bite into those pale partitions by accident, and the mouth can suddenly feel gripped, dried, and slightly punished. That contrast reveals how unevenly a fruit can distribute its chemistry. The edible seeds are designed to attract, while the rind remains more defensive, more resistant, and less inviting. It is as if the fruit presents a reward hidden inside a chemical barrier. For traditional uses, that astringency made the peel valuable in its own right, not as dessert, but as a material of potency and extraction. So the pomegranate is not simply a treasure chest of sweetness. It is layered like a fortress, with a tart, brilliant center protected by tissues whose chemistry is built to hold the world at a distance. Some desert plants store protective compounds strong enough to deter sunlight. In deserts, danger does not only crawl, bite, or infect. It also shines from above. Intense sunlight can damage tissues, disrupt vital chemistry, and push living cells toward breakdown. Some desert plants answer by building potent protective compounds into their skins, waxes, and outer tissues, creating a kind of chemical shield against ultraviolet stress and heat. These substances may absorb harmful radiation, neutralize damaging byproducts, or help stabilize the plant's own delicate systems under relentless exposure. That means the plant is not merely enduring the sun. It is chemically negotiating with it every day. Often the leaves are small, silvery, resinous, or deeply scented, physical signs of a life spent defending against brightness itself. To us, a desert shrub may look motionless and tough. In reality, it is running a constant chemical defense against one of the harshest conditions on Earth. Its extracts are not only for insects or disease. They are part of a survival strategy against light. Plants can hide toxic extracts safely until a predator bites. Some of the smartest defenses in the plant world depend on timing. A toxin can be dangerous to the plant itself if it is active in the wrong place. So many species store the ingredients separately until an animal bites, chews, or tears the tissue. Only then do broken cells allow enzymes and precursors to meet, creating the harmful compound at the moment it is needed. It is a remarkable strategy. The plant avoids poisoning its own living systems, yet keeps a potent deterrent ready for instant deployment. For the attacker, the experience can be bitter, burning, sickening, or worse, and it begins only after the damage is done. That makes the leaf or seed something like a chemical puzzle box, harmless looking on the outside, dangerous only when forced open. In this way, a bite becomes the trigger. The predator activates the very defense meant to stop it, and the plant turns injury into a sudden act of retaliation. Mustard's fierce sting appears only when its tissues are broken. A mustard seed seems small and almost inert, yet its true force waits behind a chemical lock. Inside the intact tissue, the crucial ingredients are kept apart. Crush the seed, crack the cells, and the pieces finally meet. An enzyme begins working on stored compounds, creating pungent molecules that surge upward into the nose with that unmistakable hot, sharp sting. This is why mustard can feel so alive when freshly ground or mixed. The heat is not built like chili heat, which comes ready-made in the fruit. It is generated in the moment by damage. The plant's defense is therefore activated by attack itself. That is part of what makes mustard so fascinating. The seed does not merely contain flavor. It contains the potential for flavor, waiting for friction, moisture, and rupture to bring it into being. A bland-looking grain suddenly becomes fierce, proving once again that plant extracts often reveal their most dramatic character only when disturbed. Horseradish and wasabi rely on the same chemical ambush strategy. Horseradish and wasabi feel explosive in a very particular way. Their heat rushes upward into the nose, floods the head, then fades more quickly than chili. That shared experience comes from a similar strategy hidden in their tissues. Like mustard, they store key ingredients separately until the root or stem is cut, grated, or crushed. Once the cells break, enzymes rapidly create pungent compounds called isothiocyanates, and the famous sharpness appears almost instantly. This is why freshly grated wasabi feels so vivid, and why horseradish seems strongest right after preparation. The plant is not storing ready-made fire. It is setting a trap that springs when damaged. For a grazing animal or attacking microbe, that sudden burst is a deterrent. For humans, it becomes culinary theatre. A root that looked plain and calm a moment earlier turns intense enough to make eyes widen and breath catch. It is chemistry as ambush, unleashed exactly when the plant is wounded. Onions make eyes water through a rapid burst of sulfur chemistry. Slice into an onion, and the calm kitchen can turn dramatic within seconds. Eyes sting, tears appear, and suddenly the plant seems to have reached out and acted on the body directly. That response comes from a fast sulfur-based reaction triggered by cutting. In the intact onion, certain compounds and enzymes remain safely separated. Once the cells are broken, they combine and produce a volatile irritant that rises into the air. When it reaches the moisture on the surface of the eyes, it forms substances that sting enough to trigger tearing. The tears are not sentiment. They are defense, the body trying to wash away the intruder. What makes this so captivating is the speed. A solid bulb on the board becomes an airborne weapon almost at once. The onion does not move, yet it can still fight back. In one swift chemical event, an ordinary vegetable turns preparation into an encounter with living sulfur chemistry. Plant extracts can change dramatically with soil, season, and rainfall. A plant is never making its chemistry in a vacuum. Everything around it helps shape the final result. Soil minerals can influence growth and stress. Rainfall can determine whether the plant builds lush tissue or concentrates its protective compounds. Temperature, sunlight, and season can all push the chemical balance in new directions. That means the same species may not smell, taste, or perform quite the same from one year to the next. A medicinal herb grown in a dry season may carry a different profile from one raised through steady rain. A resinous shrub on poor stony ground may produce a more intense aroma than its cousin in richer soil. This is one reason plant extraction has always carried an element of place. The environment is not a backdrop. It is part of the formula. What we call the extract is often the plant's response to its conditions, written into chemistry and preserved in leaf, bark, flower, or root. The same herb can smell different when grown on another hillside. Move a familiar herb from one hillside to another, and its identity may shift more than most people expect. Even when the species remains the same, small changes in elevation, drainage, sunlight, wind, and soil can push the plant to produce a noticeably different aromatic balance. One patch of thyme or rosemary may smell sharper, sweeter, greener, or more resinous than another, grown only a short distance away. This is part of the deep fascination of plant extracts. They carry geography inside them. A slope facing the morning sun may dry quickly and stress the plant in one way. A cooler, damper hillside may encourage another chemical emphasis entirely. To the nose, those environmental differences become real and memorable. The herb is still itself, yet it speaks with another accent. That is why growers, cooks, and distillers pay such close attention to place. They are not only cultivating plants, they are cultivating how landscape becomes aroma. Morning harvests can capture different extracts than evening harvests. Plants do not smell and taste exactly the same all day long. Their chemistry rises and falls with light, heat, water movement, and the timing of biological tasks such as pollinator attraction or daytime defense. That means harvest hour can matter. Leaves or flowers gathered in the cool of morning may preserve volatile compounds that would partly dissipate by afternoon heat. In other cases, a plant may build up certain aromas through the day and reach a stronger profile later on. This shifting rhythm gives harvesting a quiet drama. The person cutting the plant is not only choosing the right species and place, but the right moment in the daily cycle. For delicate aromatic crops, timing can influence fragrance, flavor, and extract quality in surprising ways. It is one more reason plant chemistry feels alive rather than fixed. The field at sunrise is not chemically identical to the same field at dusk. Time itself becomes part of the harvest. Drought can make some medicinal plants chemically more intense. When water becomes scarce, many plants do not simply weaken. Some respond by concentrating the very compounds that help them survive stress, defend themselves, or reduce damage from heat and dryness. As tissues grow smaller, tougher, or more resinous, certain aromatic and bioactive molecules may become more prominent. That can make a drought-grown plant smell stronger, taste sharper, or yield a more concentrated extract than the same species raised under easier conditions. It is a striking reversal of what many people expect. Hardship can sometimes intensify chemistry rather than erase it. Of course, too much stress can still stunt or kill, but within a certain range, the plant may answer scarcity with potency. This is why growers of medicinal and aromatic plants often pay close attention to water conditions. They know that comfort and character are not the same thing. A plant pushed by dryness may end up carrying the chemical marks of that struggle in every leaf, resin, and root. Young leaves and old leaves often produce different protective extracts. A plant does not defend every leaf in exactly the same way, because not every leaf faces the same risks. Young leaves are tender, nutrient-rich, and especially attractive to herbivores, so many plants load them with strong protective chemistry while they are still soft and vulnerable. Older leaves may become tougher, thicker, or less valuable to the plant over time, and their chemical priorities can shift accordingly. This creates a surprising kind of age difference within one organism. The newest growth may be brighter, more bitter, more aromatic, or more toxic than the mature foliage beside it. To a grazing insect, that difference can mean the choice between feast and warning. To humans, it can affect flavor, extraction, and medicinal use in subtle but important ways. A plant is therefore not chemically uniform from tip to base. Its defenses move with its age, protecting the tissues that matter most at the moment they are easiest to lose. A flower's scent can strengthen at night for nocturnal pollinators. Not all flowers release their richest perfume under the noon sun. Some wait for dusk. As evening falls, their scent intensifies and begins to travel through cooling air, aimed not at daytime bees but at moths, bats, and other night-active pollinators. These visitors rely heavily on smell when light is low, so the plant shifts its strategy accordingly. White or pale petals may glow in moonlight, while the fragrance does the rest of the work, guiding the right creatures toward nectar and pollen in the dark. This timing gives certain flowers an almost theatrical quality. By day, they seem quiet. By night, they awaken chemically. The garden after sunset is therefore not just a dim version of the daytime garden. It can be a different communication system altogether, built on drifting aroma rather than bright color. A flower that seems modest at noon may become magnetic after dark, proving that plant scent follows schedules as carefully as stars do. Some orchids mimic insect pheromones using exquisite chemical precision. Some orchids have evolved one of the most astonishing tricks in the plant world. Instead of offering nectar as a reward, they imitate the scent of female insects with extraordinary chemical accuracy. A male bee or wasp detects the signal, believes a mate is nearby, and rushes in. In the confusion, he attempts to mate with the flower and leaves carrying pollen. The orchid gains pollination without paying the cost of producing food. This is deception at the molecular level, and it works only because the plant's chemistry is precise enough to fool an animal whose survival depends on recognizing the right scent. The petals may even resemble the body of the insect, but the real lure is often invisible and airborne. That is what makes the story so captivating. A rooted plant, unable to chase or choose, learned instead to counterfeit desire itself. Few plant extracts are more dramatic than those that can hijack instinct in the service of reproduction. Plants can summon predators by releasing extracts after being attacked. When a plant is chewed by caterpillars or pierced by other herbivores, it does not always respond alone. Some species release airborne compounds that act like distress beacons, drawing in predators or parasites that attack the creatures doing the damage. In effect, the plant recruits bodyguards. A wasp may follow the signal to a feeding caterpillar, lay eggs on or inside it, and turn the attacker into a resource for the wasp's young. This is one of the most startling examples of how active plant chemistry can be. The plant is not merely enduring injury. It is changing the behavior of the wider ecosystem in response. The air around damaged leaves becomes a message, and nearby animals read it. That means a simple act of feeding can trigger a chain of events the herbivore never intended. A leaf under attack suddenly becomes the source of a call for help, and predators arrive because the plant has chemically asked them to. Corn seedlings can call for help with airborne chemical messages. Even a young corn plant can do far more than passively wait to be eaten. When attacked by certain insects, corn seedlings release volatile compounds into the air, and those signals can attract parasitic wasps that hunt the pests responsible. The wasps follow the scent, locate the caterpillars or larvae, and help reduce the damage. What makes this so remarkable is the scale. We are not talking about towering trees or ancient shrubs, but tender seedlings only beginning their lives. Yet even at that stage, they are capable of chemical communication sophisticated enough to recruit another species as an ally. The field becomes a place of invisible signals and responses, not just green rows under the sky. To human eyes, the corn may look silent. In chemical terms, it is speaking urgently when under attack. A seedling rooted in soil can still alter the outcome of its own survival by sending help signals into the air around it. Damaged sagebrush can warn nearby plants through drifting compounds. A wounded sagebrush does not keep the news to itself. When browsed or damaged, it can release airborne compounds that drift to neighboring plants, and those plants may respond by increasing their own defenses before the threat reaches them. This is one of the clearest examples of a plant community acting less like isolated individuals and more like a network of listeners. The message travels on the wind, not in words but in chemistry, and nearby leaves read it as a warning to prepare. That readiness may mean producing more bitter compounds, more defensive proteins, or other changes that make the next bite less rewarding. The idea is extraordinary. A plant attacked in one spot can influence the physiology of another standing several feet away. The landscape begins to seem far less silent than it appears. What looks like still vegetation is often full of signals moving between neighbors, with sagebrush serving as one of the best-known messengers. Walnut trees can chemically sabotage neighbors with juglone. A walnut tree does not compete only with shade and roots. It also releases juglone, a compound that can make life much harder for certain nearby plants. Juglone can seep into the soil from roots, fallen leaves, husks, and decaying wood, creating a zone where some species struggle to germinate, grow, or even survive. The effect is not universal, which makes it even more fascinating. Some plants tolerate it well, while others wilt as though the ground itself has turned against them. This means a walnut tree can shape its surroundings without moving an inch, altering the community below it through chemistry alone. To a person walking past, it may look like ordinary woodland spacing. In reality, the tree may be quietly editing the neighborhood, discouraging rivals and protecting access to light, water, and nutrients. It is a reminder that some landscapes are arranged not just by climate and soil, but by invisible acts of botanical pressure. Eucalyptus litter can shape entire landscapes through chemical fallout. When eucalyptus leaves fall, they do not become harmless debris. They carry aromatic oils and other compounds down to the ground, where rain, decay, and contact begin spreading that chemistry through the soil surface. This falling litter can suppress germination in some species, slow the growth of others, and change how quickly the leaf layer itself breaks down. Over time, that influence can shape the look and feel of an entire grove. The understory may thin. Certain plants may fail to establish. The forest floor can become dominated by a particular texture and scent, built not just by shade but by chemical residue accumulating year after year. That is part of what makes eucalyptus landscapes so distinctive. The trees do not stop acting when their leaves die. Their chemistry keeps working after the fall, drifting from canopy to ground and helping determine what kind of community can live beneath them. It is ecological fallout, leaf by leaf. Many weeds succeed because their extracts disrupt other species. Some weeds do not win simply by growing fast or scattering seeds widely. They also bring chemical interference into the struggle. Through roots, leaves, or decomposing litter, certain aggressive plants release compounds that hinder the germination or early growth of nearby species. This gives them a head start in the race for light, water, and space. The tactic is especially effective in disturbed ground, where seedlings are vulnerable and competition is fierce. A patch of invasive growth can therefore become more than a crowd. It becomes a chemically difficult place for rivals to establish themselves. That helps explain why some weeds seem to take over with startling efficiency, spreading across roadsides, fields, and abandoned lots, as if the land itself has chosen them. In truth, they may be helping make that choice. Their success is not only about surviving the environment, it is about subtly changing the environment around them so other plants have a harder time surviving too. Plant resins are sticky chemical fortresses against insects and fungi. Resin is one of the plant world's most satisfying defenses because it solves several problems at once. It is sticky enough to trap or deter insects, thick enough to seal wounds, and chemically rich enough to discourage fungi and microbes from invading damaged tissue. When bark is pierced or stems are broken, resin can flow outward like a living cork, closing the breach before the plant loses too much water or becomes infected. That means a tree or shrub is not relying on one line of defense. It is using a material that blocks, glues, suffocates, and chemically repels at the same time. To us, dried resin can look beautiful, golden and fragrant. To the plant, it is emergency armor. In hot climates or insect-heavy forests, that armor can make the difference between recovery and decline. Few extracts show such practical elegance. A glossy ooze from a wound becomes a miniature fortress, built in real time exactly where danger enters. Frankincense begins as a tree's fragrant wound-sealing resin. Frankincense starts with injury. When the bark of certain boswellia trees is cut, resin slowly seeps out to seal the wound and protect the tree from infection and water loss. At first it is soft and sticky, but as it dries it hardens into pale, tear-shaped drops that can be gathered by hand. Those tears carry an aroma unlike most other plant extracts, bright, resinous, citrus-touched, and deeply ancient in feeling. For thousands of years, people burned it in temples, traded it across deserts, and treated it as something worthy of ceremony and distance. Yet beneath all that human reverence lies a simple botanical truth. The substance began as defense. It was the tree's response to damage, a fragrant patch over vulnerable tissue. That is part of why frankincense feels so compelling. One of history's most sacred aromas comes from a plant trying to heal itself, turning a wound into something people later associated with prayer, mystery, and smoke. Myrrh was treasured because its bitter aroma came with preserving power. Myrrh does not charm in the same way as rose or citrus. Its scent is darker, more medicinal, more solemn, with bitterness built right into the experience. That serious character reflects the chemistry of a resin shaped by protection. Drawn from wounded Commiphora trees, myrrh contains compounds that helped make it valuable not just as fragrance, but as a substance associated with preservation, ritual, and care. In the ancient world, that mattered enormously. A material that smelled distinctive and resisted decay seemed to sit at the border between the living and the sacred. It could perfume, protect, and endure. That is why myrrh moved through trade routes and burial practices with such prestige. People were not merely collecting a pleasant smell. They were handling a resin whose bitterness suggested strength and whose properties made it useful where time, corruption, and mortality pressed hardest. Few plant extracts carry so much gravity in such a small, aromatic tear of dried resin. Amber began as plant resin long before it became fossil treasure. Before amber became a polished gem holding ancient insects and sunlight like memory, it was simply resin oozing from wounded trees. Sticky, aromatic, and defensive, it flowed to seal bark and protect living tissue from attack. In that first stage, it belonged entirely to the plant's present. Then time took over. Buried, compressed, and altered over immense spans, some of that resin hardened and fossilized into amber, carrying within it a transformed version of plant chemistry from vanished forests. This gives amber a rare double life. It begins as a practical wound response, then becomes a geological relic treasured for beauty and age. When people hold a piece of amber, they are touching the afterlife of a plant extract. Its golden clarity and occasional trapped fragments of ancient life make it feel almost supernatural, yet its origin is humble and biological. A forest defense, preserved beyond the lifespan of the tree, becomes a jewel of deep time. Rubber started as a plant latex with extraordinary defensive chemistry. Long before rubber became tires, hoses, gloves, and bouncing balls, it flowed as latex inside living plants. This milky fluid is not sap in the ordinary sense. It is a defensive cocktail carried in specialized channels, ready to surge out when the plant is cut or bitten. Once exposed to air, it can thicken, gum up mouthparts, and physically hinder attackers, while additional compounds inside it may taste bad or prove toxic. For the plant, latex is both trap and warning. For humans, it became one of the most transformative natural materials ever discovered. People learned to tap rubber trees, collect the latex, and eventually process it into elastic products that changed transport, industry, and daily life across the world. What makes the story so remarkable is the leap from ecology to technology. A substance evolved to frustrate insects became essential to machines, medicine, and modern movement. Defense chemistry, drawn from bark, ended up rolling civilization forward. Opium poppies produce alkaloids that profoundly alter pain and consciousness. Inside the poppy capsule lies one of the most consequential chemical arsenals ever evolved by a plant. The milky latex of the opium poppy contains alkaloids that can relieve pain with astonishing power, but also alter mood, awareness, dependence, and human history itself. Morphine, codeine, and related compounds act on the nervous system in ways that can quiet suffering so deeply that medicine was permanently changed once people learned to isolate and use them. Yet the same chemistry carries enormous danger. Relief can slide into addiction, and sedation can become fatal when the dose overwhelms the body. That tension is what makes the poppy so gripping as a subject. It is not merely a medicinal plant and not merely a poisonous one. It sits at a crossroads of mercy, pleasure, commerce, conflict, and grief. Few extracts reveal more starkly how one plant can hold both compassionate power and devastating consequence in the same pale flow of latex. Coca leaves contain extracts that changed medicine and world history. For peoples of the Andes, coca leaves were part of daily life long before the wider world took notice. Chewed with alkaline substances, they could ease hunger, reduce fatigue, and help people cope with high altitude. The leaves held a set of alkaloids, among them cocaine, that would later move from traditional use into medicine, industry, and global upheaval. In purified form, that chemistry became a local anesthetic of major importance, allowing doctors to numb tissue in ways that opened new possibilities in surgery and dentistry. But it also fed addiction, illicit trade, violence, and political turmoil on a vast scale. That is the extraordinary reach of one plant extract. A shrub adapted to mountain life ended up touching hospitals, criminal networks, empires, and international law. The leaf itself did not change. Human systems around it did. Few plants have sent chemistry outward with such different meanings, from endurance and treatment to exploitation and conflict. Curare began as a plant-based arrow poison. Deep in the forests of South America, hunters learned to prepare one of the most elegant and terrifying uses of plant chemistry ever devised. Curare was made from a mixture that often included extracts from certain vines and other plants, then applied to arrows or darts. Once it entered the body, the poison could interfere with the signals between nerves and muscles, causing paralysis, while leaving awareness terrifyingly intact until breathing failed. For hunting, this meant a small wound could bring down prey efficiently. For science, it later became something else entirely. Researchers studied curare-like substances and learned from their effect on the neuromuscular system, eventually developing related compounds used in modern medicine to relax muscles during surgery. That arc is astonishing. A forest poison prepared for survival and skill at the edge of the canopy helped reveal fundamental truths about the human body. Few extracts travel such a dramatic path from arrow tip to operating room. Atropine from deadly nightshade can widen the human pupil. Deadly nightshade has long carried an aura of menace, and not without reason. Among its powerful compounds is atropine, a substance capable of affecting the nervous system in striking ways. One of its best-known actions is to widen the pupil, making the dark center of the eye open larger than usual. That effect once fed beauty practices, which is both fascinating and unsettling. A plant feared for toxicity was used to create an appearance of allure by temporarily altering vision and eye function. Today, atropine has legitimate medical uses, especially in eye care and certain emergencies, because doctors can harness that same physiological effect with precision. What makes it so compelling is how directly it reaches into the body's automatic controls. This is not a fragrance or a flavor working gently at the surface. It is a molecule capable of changing the eye's response to light itself, drawn from a plant whose name still warns of danger. Yew tree compounds helped inspire powerful cancer treatments. The yew tree does not look like a medical revolution. It stands dark, patient, and ancient, often associated with churchyards, hedges, and winter berries. Yet within its tissues, scientists discovered compounds that led to some of the most important cancer treatments ever developed from plants. These molecules work by interfering with the machinery cells use when they divide, which made them powerful tools against rapidly growing tumors. The path from tree to treatment was not simple. The chemistry was difficult, the sourcing raised serious questions, and researchers had to find ways to produce needed substances without stripping ancient trees from the landscape. But the result was profound. A plant known for toxicity and longevity became part of modern oncology. That alone is enough to stop people in their tracks. A quiet evergreen, rooted in old graveyards and hedgerows, ended up helping wage one of medicine's hardest battles. Few trees carry such a dramatic hidden legacy inside their needles and bark. Madagascar periwinkle changed leukemia care with plant-derived alkaloids. Madagascar periwinkle looks almost too cheerful for the gravity of its story. With its neat petals and garden-friendly appearance, it seems like a decorative plant first and foremost. Yet inside it were alkaloids that helped transform the treatment of certain blood cancers, especially childhood leukemia. These compounds interfere with cell division, and once researchers understood their power, they became part of therapies that dramatically improved survival. That shift changed countless families' futures and gave one ornamental plant a place in the history of life-saving medicine. The contrast is unforgettable. A flower growing quietly in warm climates or garden beds carried chemistry capable of reaching into one of the most serious diseases known. This is one of the reasons plant extracts remain so compelling to medicine. Their appearances can be misleading. A bloom chosen for beauty may also contain a molecule strong enough to alter the odds between illness and recovery in the most profound way imaginable. Artemisia gave medicine one of its most important anti-malarial compounds. Malaria has shaped human history with relentless force, so any truly effective weapon against it matters far beyond the laboratory. One of the most important came from Artemisia annua, a plant whose chemistry yielded artemisinin, a compound that became central to modern malaria treatment. Its discovery was a major turning point because it offered powerful action against a disease that had outmaneuvered countless efforts across centuries. What makes the story especially compelling is that the answer emerged from plant knowledge, careful extraction, and scientific persistence working together. The compound acts quickly against the malaria parasite, and its use in combination therapies has helped save enormous numbers of lives. That is the extraordinary reach of one botanical extract. A plant growing with feathery leaves and modest presence became part of a global defense against fever, anemia, and death. Few examples show more clearly that the future of medicine can still arrive from the hidden chemistry of leaves. Cinchona bark became so valuable, it reshaped empires and trade. There are moments in history when a plant extract becomes more than a remedy and starts altering the map itself. Cinchona bark was one of those cases. Once people understood that its bitter compounds could help treat malaria, the bark became immensely valuable to nations seeking to move, govern, and survive in tropical regions where fever had long resisted control. Demand surged. Trees were hunted, transplanted, cultivated, and fought over. Knowledge about the bark's chemistry became a strategic advantage, and access to plantations mattered to empires in ways that reached far beyond medicine. This is what makes Cinchona so extraordinary. It was not only a tree in the Andes, and not only a source of quinine. It became part of the machinery of exploration, colonization, trade, and power. Few barks in history have carried such geopolitical weight. A bitter extract under the skin of a mountain tree helped determine who could travel, who could stay, and who could rule. Indigo dye came from plant extraction long before synthetic chemistry. Long before chemists learned to build color in factories, people were already coaxing one of the world's most famous blues from plants. Indigo did not begin as a bright pigment waiting on the leaf surface. It had to be developed through cutting, soaking, fermenting, beating, and exposing plant extracts to air until the color emerged and deepened. That process turned fields of green leaves into vats of blue potential, and from there into cloth so striking it became associated with status, labor, trade, and identity across continents. Indigo's story is remarkable because it joins agriculture, microbial transformation, craft, and fashion in one long chain. The color people came to treasure was the final act of a carefully managed chemical drama. Without extraction and oxidation, the blue would not appear in the same way. What seems like a simple dye is therefore a triumph of early chemical understanding, discovered and refined long before the age of modern industry. Henna stains skin because its pigment binds stubbornly to protein. Henna does not merely sit on the skin like paint. Its active pigment, losone, binds to proteins, especially the keratin in skin, hair, and nails, which is why the stain can persist even after repeated washing. That simple fact gives henna its enduring magic. A leaf can be dried, powdered, mixed into paste, and then used to leave intricate reddish-brown patterns that seem to grow warmer over time as the stain develops. The color is temporary, yet it clings with enough determination to feel almost like a conversation between plant and body. Across cultures, henna has marked celebrations, rites of passage, beauty practices, and daily adornment, all because one plant pigment happens to hold onto human tissue with remarkable loyalty. What fascinates many people is how intimate the process feels. The design is not laid on the surface alone. It becomes part of the outer body for a while, carried by the chemistry of leaf and protein meeting. Paprika color comes from plant pigments that also harvest sunlight. The red and orange tones in paprika look purely decorative once they reach a kitchen shelf, yet they begin as pigments with a vital job inside the pepper itself. These compounds belong to the carotenoid family, which helps plants manage light and support the machinery of photosynthesis. In the living fruit, that means helping handle solar energy and protecting tissues as the pepper ripens from green toward brilliant color. When the peppers are dried and ground, those same pigments become flavor's visual partner, turning oils, stews, sausages, and sauces into something warmer before the first bite is even taken. This gives paprika a wonderful double identity. It is both sunlight management turned inward and culinary color turned outward. The spice's glow is not accidental ornament. It is the preserved chemistry of a fruit that used pigments to live and mature on the plant. What shines in the pan once helped the pepper face the sun. Beetroot extract can stain food with astonishing strength. Cut into a beet and the knife itself seems to tell the story. Surfaces redden immediately. Fingers stain. Water clouds pink. The intensity comes from betalains, pigments so vivid that a small amount of beetroot extract can transform a whole dish with ease. This strength makes beet color feel almost theatrical. A pale batter can turn rose red. Rice can blush. Frosting can become startlingly bright without the help of synthetic dye. Yet the power is fragile in its own way, because heat, acidity, and time can all shift how that color behaves. That delicate balance adds to the fascination. The pigment is strong enough to dominate a cutting board, yet sensitive enough to change character under different cooking conditions. Beetroot, therefore, offers one of the clearest demonstrations that plant extracts are not passive ingredients. They are active players in the kitchen, reshaping color, mood, and expectation the moment they are released from the root. Annotto seeds color cheeses and butter with tropical plant pigment. Annotto comes from the seeds of a tropical shrub, and few natural colorants have traveled so far into everyday food without most people noticing. The seeds are coated with pigments called bixin and norbexin, which can stain oils, cheeses, butter, rice, and sauces, with shades ranging from golden yellow to deep orange. That vivid effect is why Annotto became useful anywhere food needed warmth of color without overwhelming flavor. The chemistry is fascinating because the seed itself is small and hard, almost modest, yet its surface carries enough pigment to tint whole batches of food. In some places, Annotto became part of regional identity, giving certain cheeses and dishes their familiar look. What makes it so compelling is the contrast between source and result. A tiny tropical seed can shift the visual mood of a meal instantly. It proves once again that plant extracts do not just change taste and aroma. They also teach the eye what to expect. Chlorophyll extracts glow red under the right kind of light. Chlorophyll is famous for making plants green, but under the right conditions it reveals a stranger side. Shine certain wavelengths of light onto chlorophyll extracts, and instead of returning green, they can fluoresce red. It feels almost impossible the first time you see it. The pigment that helps capture sunlight for photosynthesis suddenly answers with a hidden crimson glow. This happens because chlorophyll absorbs energy, and when it can no longer pass that energy into the machinery of a living plant, some of it is released again as red light. That means the glow is not decorative. It is a clue to how the pigment handles energy itself. In the leaf, chlorophyll is part of one of the most important processes on Earth. In the extract, removed from that living context, it can expose an eerie optical secret. A green plant pigment becomes a red lantern, and the ordinary leaf begins to seem much more mysterious. Some plant pigments change color depending on acidity. Not every plant pigment is loyal to one shade. Some are chemically sensitive enough to shift their appearance when the surrounding acidity changes, turning the same extract red in one setting, purple in another, and blue or green in yet another. That means color in the plant world is sometimes less like paint and more like mood. The molecule remains related to itself, yet the environment around it changes how it handles light. This is part of what makes plant chemistry so astonishing. A pigment can behave like an instrument, tuning itself to invisible conditions. In the kitchen, the effect can appear in fruits, flowers, or vegetables whose colors deepen or drift when mixed with acidic juices or alkaline ingredients. In nature, it helps create the extraordinary range of hues seen in petals, skins, and leaves. What seems like a fixed visual identity can turn out to be chemically flexible, responsive, and almost theatrical in the way it transforms. Red cabbage can act like a natural chemical indicator. Cook red cabbage, simmer the leaves, and the dark purple water that appears is more than colored liquid. It is a natural indicator, capable of shifting through red, pink, violet, blue, and green, depending on the acidity or alkalinity of what it meets. Few kitchen ingredients reveal chemistry so dramatically. Add lemon juice, and the color moves toward red. Stir in something more alkaline, and it can slide toward blue or green. Suddenly, a vegetable becomes a laboratory tool. The reason lies in its pigments, which respond to the chemical environment with visible changes in how they reflect and absorb light. This makes red cabbage wonderfully educational, but also deeply enchanting. A pot on the stove can begin to feel like an experiment in hidden forces. The plant is showing that color is not always static. Sometimes it is a message about chemistry itself, written in liquid purple and shifting before your eyes in real time. Anthocyanins paint berries blue, purple, red, and almost black. The deep shades of blueberries, blackberries, cherries, plums, and many other fruits often come from anthocyanins, a family of pigments with extraordinary range. These compounds can produce tones from bright red to wine, purple to blue, so dark it nearly reads as black. That richness gives berries much of their visual allure, making them look ripe, sweet, and full of concentrated flavor before a bite is ever taken. Yet anthocyanins are doing more than decorating fruit for human admiration. In the plant, they can help attract animals that will eat the fruit and disperse the seeds, while also playing protective roles in living tissues. Their color can shift with acidity, structure, and the company of other molecules, which is why the same family of pigments can create such different effects across the plant world. A berry's skin is therefore not simply painted. It is chemically composed, using molecules that turn ripeness into one of nature's most luxurious visual signals. Carotenoids give carrots color while helping plants manage excess light. The orange of a carrot looks almost playful, but the pigments behind it belong to a serious botanical system. Carotenoids help plants handle light, especially when sunlight becomes more intense than the photosynthetic machinery can safely use. They assist in harvesting energy, but they also help manage overload, protecting tissues from damage when brightness becomes too much. In carrots, those pigments accumulate so strongly in the root that they create the familiar orange people know at a glance. That means a color associated with soup, cake, and lunchboxes is connected to one of the plant world's great strategies for living under the sun. The root stores what the plant has made, and humans later harvest the visible result. This gives the carrot a quiet elegance. Its color is not random decoration. It is the preserved signature of a pigment system built for survival and balance in light. What glows on the cutting board once helped the plant negotiate sunlight itself. Plant extracts can protect seeds for years inside dry storage. A seed's future depends on surviving the long wait between one generation and the next. For some species, that means carrying protective extracts inside the seed coat or surrounding tissues, where they help defend against insects, microbes, and decay during months or even years of dormancy. In dry storage, those compounds may remain surprisingly effective, standing guard while the embryo inside stays inactive and vulnerable. This is one reason some seeds can endure long stretches of time without losing all hope of life. They are not simply asleep. They are provisioned. The chemistry packed around them helps reduce the chances that fungi or bacteria will claim them before rain and warmth arrive. It is a remarkable arrangement. A seed small enough to sit on a fingertip may contain a whole survival plan, including defenses designed to protect the next generation in silence and darkness. Even waiting, in the plant world, is supported by chemistry. Some seeds carry antimicrobial compounds to guard the next generation. A seed is one of the most vulnerable promises in nature. It contains concentrated nutrition and the blueprint for a future plant, which makes it an attractive target for microbes looking for an easy meal. To counter that threat, some seeds carry antimicrobial compounds in their coats, storage tissues, or surrounding fruits. These extracts help suppress fungi, bacteria, and other organisms that might invade before germination ever begins. In effect, the parent plant sent its offspring into the world with a chemical guard already in place. That is one reason seeds can seem so durable despite being biologically precious. Their protection is not only physical, it is molecular. The outer shell, the bitterness, the resinous note, or the unusual chemistry may all be part of a defense designed for the first and most defenseless stage of life. Before the root emerges and before the first leaf finds light, the seed may already be fighting to survive with extracts packed around its sleeping future. Resin-rich woods can survive decay far longer than expected. Some woods seem almost stubborn in the face of time. They resist rot, endure dampness, and remain sound far longer than many other timbers would under the same conditions. Often that resilience comes from high resin content. The same sticky defensive chemistry that protects a living tree from insects and invading microbes can continue offering protection after the wood is cut. Resin-rich tissues are less welcoming to fungi, slower to absorb damage, and harder for many organisms to break down. That is why certain woods earned reputations for durability in ships, buildings, tools, and outdoor structures. Their chemistry gave them longevity that felt almost like a character trait. The tree's old defense system remained active in a new form, helping the dead wood outlast expectation. This makes timber less inert than it seems. Even after the tree is gone, its extracts can keep shaping the material's fate, proving that plant chemistry can extend its influence long beyond the living trunk. Certain flowers smell sweetest exactly when their pollinators arrive. A flower's perfume is often timed with astonishing precision. Some species release their richest scent only during the window when their most important pollinators are active, whether that means early morning bees, dusk flying moths, or bats moving through the night. This is more than coincidence. Producing fragrance takes energy, so the plant benefits by concentrating its aromatic effort when it is most likely to matter. That gives the bloom a schedule, one tuned to the habits of another living creature. The result can feel almost magical to us. A flower may seem faint at 1 hour, then suddenly bloom into fragrance later, as if it had been waiting for an appointment. In truth, that is not far from reality. The scent is part of an ecological meeting arranged by time. What humans experience as sweetness in the air is often the plant's carefully timed invitation, released at the exact moment the right visitor is most likely to arrive. Perfume makers chase plant extracts because living scents are chemically layered. Real plant scents are rarely simple. A rose, jasmine, citrus blossom, or patch of crushed leaves may seem to present one clear fragrance at first, yet each is usually built from many molecules arriving at different speeds and fading on different pH. Schedules. Some notes leap into the air immediately. Others stay close and unfold more slowly. Some brighten the scent. Others deepen it, soften it, or give it shape in a way the nose registers without easily naming. This layered complexity is why perfume makers have always pursued plant extracts with such intensity. They are not merely capturing one pleasant smell. They are trying to preserve a living architecture of aroma. That challenge is part of the romance of perfumery. Nature rarely offers flat fragrance. It offers movement, contrast, and depth. A flower's scent can open like music, one part rising first, another arriving later, all held together by chemistry that makes the whole experience feel alive. Essential oils are not oils in the way most people think. The name can be misleading. Essential oils are called oils because they are hydrophobic and often feel slick, but they are not oils in the same way as olive oil, butterfat, or other greasy substances built mainly from triglycerides. Instead, they are concentrated mixtures of volatile aromatic compounds extracted from plants. Their character lies in fragrance, not in calories or nutrition. They evaporate far more readily, carry scent intensely, and can behave very differently from cooking or body oils. This distinction matters because it reveals what these extracts really are. They are the drifting aromatic part of plant chemistry, gathered and concentrated into liquid form. A drop may smell immense because it contains the essence of leaves, bark, peel, flowers, or resin, stripped down to its volatile core. The word oil, therefore, hides an important truth. What sits in the bottle is less like food and more like bottled vapor waiting to happen, condensed from the plant's most aromatic molecules. Steam can pull fragrance from petals without burning the chemistry. Many delicate plant aromas would suffer if treated like something to be boiled hard or scorched by direct heat. Steam distillation solves that problem beautifully. Instead of burning the petals, leaves, or peels, steam passes through them and coaxes volatile aromatic molecules into the vapor. That vapor then cools and condenses, separating into fragrant extract and scented water. It is an elegant method because it borrows heat without allowing the plant material to char. In effect, the fragrance is lifted out on a cloud. This has made it possible to capture scents from countless botanical sources in forms suitable for perfume, flavor, and ritual use. There is something almost poetic about the process. A flower does not need to be destroyed by fire to surrender its perfume. Warm vapor persuades it instead. The result feels less like crushing and more like translation, as though the scent were carried from petal to bottle by a gentler kind of chemistry. Solvents can capture aromas too delicate for heat alone. Some floral scents are so fragile that even careful steam distillation can alter them, flatten them, or leave important notes behind. In those cases, solvents offer another path. They can dissolve aromatic compounds directly from petals and other plant tissues, capturing fragrance molecules that might never survive a hotter process intact. Later, the solvent is removed, leaving behind a concentrated material that holds more of the original character. This is one reason certain perfumes feel astonishingly close to the living flower. The method can preserve aspects of softness, depth, or green nuance that heat alone might miss. It is a reminder that extraction is not one simple act. It is a choice about what kind of truth you want from the plant. Do you want the bright, volatile portion, or the richer, more faithful portrait? Solvents made it possible to chase the second kind, holding on to whispers of aroma that would otherwise disappear before they could ever be bottled. A plant extract may smell simple but contain hundreds of molecules. The nose loves shortcuts. It takes a complex cloud of chemicals and reports something manageable back to the mind. Minty, rosy, lemony, woody, green. Yet behind that apparent simplicity, there may be hundreds of distinct molecules, each contributing a tiny part of the total impression. Some create the main recognizable note. Others round it, sharpen it, sweeten it, or add shadows that most people notice only when they are gone. This is why natural scents feel so alive. They are not single ingredients pretending to be whole. They are real chemical communities. A lavender extract, for instance, may seem immediately familiar, but its identity depends on a whole arrangement of compounds arriving together in balance. Remove or alter enough of them, and the scent loses depth or turns artificial. What feels simple to the ear and the tongue is often breathtakingly crowded at the molecular level. The plant offers an orchestra, and the senses summarize it as one melody. Tiny differences in chirality can make plant aromas smell completely different. Some molecules have the same atoms connected in the same order, yet still exist in two mirror image forms. This property is called chirality, and in scent, it can change everything. One version of a molecule may smell bright and orange-like, while its mirror image smells more like pine or turpentine. Chemically, they are close enough to seem nearly identical on paper, but the nose can tell them apart because the receptors involved in smell are themselves shaped in ways that respond differently to each form. This is one of the most astonishing lessons in aroma science. The difference between one scent and another can come down not to different ingredients, but to a flipped spatial arrangement of the same one. Plant extracts, therefore, carry not only chemistry, but geometry. The exact-handedness of a molecule can help define the whole character of an oil or aroma. Nature is working in 3 dimensions, and your nose notices the slightest twist. Some plant extracts vanish quickly because they are chemically restless. Certain fragrances seem to bloom and disappear almost in the same breath. Citrus zest can brighten the air brilliantly, then fade with surprising speed. Crushed herbs can flash into life, and then soften before you realize how brief the moment was. This happens because many of the compounds involved are highly volatile and chemically restless. They evaporate quickly, react with air, or shift under light and warmth, which means the scent they create is vivid, but fleeting. That transience is part of their charm. They feel alive because they refuse to sit still. In the plant, such compounds may be useful precisely because they move fast, sending signals outward or creating an immediate defensive effect. In human experience, they become the top notes of perfume, the sparkle of zest, the first impression of freshness. A scent that fades quickly is not weak. Often, it is simply made of molecules eager to escape, transform, and disappear into the air. Others cling to skin and fabric for hours. Not all plant-derived scents behave like a bright burst that vanishes on the breeze. Some settle in, sinking into cloth, hair, wood, or skin, and remaining there for hours. These longer-lasting effects usually come from heavier, less volatile molecules that do not leap away so quickly. Resins, woods, roots, and certain deep floral materials often carry this kind of persistence. Their aromas unfold more slowly, but once established they can feel almost haunting, returning in warm pulses as body heat or movement releases them again. This is why a scarf can still smell faintly of perfume the next day, or why a room can keep traces of incense long after the smoke is gone. The plant chemistry lingers because it is built from compounds less eager to leave. That endurance gives such extracts a special role in perfumery and ritual. They are the memory keepers of aroma, staying behind after the brighter notes have already flown. The future of medicine may still be hiding in overlooked plants. For all the drugs already inspired by leaves, bark, roots, and resins, the botanical world remains vastly underexplored. Many plant species have never been studied in depth for their chemistry, and even within known species, overlooked populations, growth conditions, or obscure tissues may hold compounds no one has properly examined. This matters because plants have spent millions of years evolving molecules that interact with living systems in remarkably specific ways. They have been solving problems of defense, repair, signaling, and survival far longer than human laboratories have existed. Somewhere in that enormous green library may be future treatments for infection, inflammation, pain, cancer, or entirely different challenges we do not yet know how to solve. The thrilling part is that discovery does not always begin in a high-tech machine. Sometimes it begins with noticing the unusual, the local, the long-used, or the ignored. The next major medical breakthrough may still be growing quietly in plain sight. Plant extracts reveal that still-rooted life can be chemically astonishing. Plants can seem passive because they do not run, hunt, or shout. Yet once you begin following their extracts, a very different picture emerges. Here are organisms making coolness that is not cold, heat that is not fire, fragrance that recruits insects, pigments that answer chemistry with color, and poisons, medicines, dyes, preservatives, stimulants, and resins, all from tissues that appear still to the eye. Their lives unfold through molecules. Every root, seed, bark strip, petal, and leaf may hold a response to some ancient challenge, encoded not in movement, but in chemistry. That is what makes this world so captivating. The drama is there, just written in another language. A rooted plant can defend itself, deceive an insect, preserve a future seed, or alter a human body without ever taking a step. Once you realize that, stillness no longer looks simple. It looks like concentration, patience, and invention on a scale most people walk past every day. And now, we've come to the end of our journey through the hidden world of plant extracts. Tonight, we wandered through roots, bark, leaves, flowers, seeds, and resins, and found that stillness can hide astonishing power. We found sweetness designed to move seeds across the world. We found bitterness shaped by ancient struggles. We found perfumes drifting from petals, defenses waiting inside crushed leaves, and pigments bright enough to color food, cloth, skin, and memory itself. It's remarkable to think that so much of this world lives in silence. In a peel, a pod, a seed, or a drop of sap. There can be medicines, warnings, invitations, and transformations, all waiting to be released. The scent of a forest, the sting of mustard, the warmth of cinnamon, the glow of paprika, the calm familiarity of vanilla. Each one is part of a much older story, written by plants as they learned how to survive. And perhaps that is a soothing thought to end on. All around us, life is patient. It does not rush. It builds slowly, molecule by molecule, season by season, until an entire hidden world is folded into a single leaf or flower. If you enjoyed this sleepy journey, I'd love for you to like, subscribe, or share a thought below. It helps other curious minds find their way here too, one sleepy soul at a time. And if you happen to still be awake, there'll be another video waiting for you on screen, ready to carry you a little further into the night. But for now, let your thoughts grow soft. Let your breathing slow. And let the day drift gently away as you rest beneath the quiet, unseen chemistry of the living world. Sleep well, and good night.